Hi guys, this is the quiz video for Unit 5 in Algebra 2 DC, radicals and exponents. So this one is simplify fully into exponential form. So I see all these radical symbols, but they represent grouping symbols followed by powers on those groups. So if I want to start by getting into exponential form, I can take these radicals and replace them with the parentheses and the 1/2 power that they represent. So a square root has an invisible index of 2, and that index is what is the denominator of the exponent. So my 50x squared is, x to the 5th, 50 times x to the 5th is there, all right? Minus 6x squared, the square root gets replaced by a parentheses and a 1/2 power. Oh, did I really want to do that? I mean, yeah, but can I simplify what's in here? Because writing 8/4 kind of hurts my heart. What if I just simplify that to 2? Yeah, that's better. 8x over 4 is the same thing as 2x. Yeah, so since we're simplifying, let's simplify from the get-go. All right, this is a subtraction problem, which is a little bit weird, but we're gonna see if maybe we can find a GCF at the end, or if there's some way to factor it, that'd be great. I don't know if there will be, but let's find out. So I'm just gonna keep simplifying each term individually. This 50, now I added this to the quiz and it will be on the test, where I do not want numbers like 50 because 50 can be factored into primes. So in order to make prime bases, I need to figure out what 50 is made of. So I'm going to divide 50. Let's divide it by 5 and we get 10. I can divide by 5 again and get 2, and then I have 2 and I've got my 1. So my prime factorization of 50. 50 is equal to 5 squared times 2. So I'm going to rewrite that, 5 squared times 2, and then I have times x to the 5th, and all of that is to the 1/2 power. And over here I have 6. Okay, this one I can start talking about what I'm doing with this exponent. It gets applied to both of the factors inside of it because it is on the parenthesis. And exponents do distribute across multiplication, just not across addition. So I'm going to start with my 6x squared, but I'm also going to then, instead of the parentheses, I'm going to write 2 to the 1/2 times x to the 1/2. And now I've gotten rid of those parentheses. I've applied that 1/2 power to the things that are in it. Great. Let's keep going. I'm going to do the same thing I just did for this 1/2 power to each of the factors inside of this one. So 5 squared to the 1/2 power is 5 to the 2/2 power because I multiply them. And then that's just 5 to the 1. Now this is just going to be 2 to the 1/2 power because its current exponent is 1 and 1 times half is half. But yeah, it didn't have 1, now it does. And then this is now x to the 5/2. Okay? And then here, oh, 6 isn't prime either. I almost forgot. 6, so just like 50 can be written as 5 squared times 2, 6 can be written as 3 times 2. I didn't need a factor tree for that. So I'm going to rewrite this as 3 times 2 times, well, there's another 2 here I'm going to bring forward to sort of see that those are maybe going to combine. And then I have x squared times x to the 1/2. Well, watch video A if you want to see the full explanation, but we know that x squared times x cubed is x to the 5th. Because that's 2x, x times x times x times x, right? So I normally am adding those exponents to make the new exponent. So when I see this as well, x to the something times x to the something is going to be x to the first exponent plus the second exponent. So x to the 2 plus a half, that's 4 halves plus 1 half is 5 halves. Oh, I've seen 5 halves before. Oh yeah, there it is. Interesting. Oh, I was about to combine these, but I got a couple of different ideas of where this could go from here, because it's subtraction. So I was always kind of, as working through these problems, right, this is equals, I was always kind of thinking about what would be able to factor. And I just noticed a pair of common factors. If I factor those out, so if I take my 2 to the 1 half times x to the 5 halves, and that's one side of my box, right? I could think of this as a box situation, where I put my 5 times 2 to the 1 half times x to the 5 halves. That leaves a 5 up here, right? When I put my 2 to the 1 half x to the 5 halves. And over here I have negative 3 times 2 to the 1 half times x to the 5 halves. Oh, so that's minus, well, 3 times 2 is 6. Ha ha ha. Ho 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 ho. It's not just factoring out a GCF, it's combining like terms. So there's 5 of this minus 6 of this makes negative 1 of that. Crazy. This simplifies a lot. So to finalize that and put it just in official form, I want to put the negative out front, the 2 to the 1 half, and the x to the 5 halves, just because that's convention. So this is my final answer for the fully simplified exponential form with only prime numerical bases. There's no radicals in it. There's no repeated bases. I factored it so that I could fully simplify it and recognize those like terms that combined. Great, that was awesome. Now, could I have recognized that maybe even sooner if I had left it in radical form? Maybe. If I had simplified it in radical form, because it's just square roots, I'm pretty comfortable with those. I might have noticed that square root of 2 times x to the 5 halves. Well, in radical form, this is the square root of 2x, and this would be x squared outside. This would have been the radical form that I would have had 5 of here minus 6 of there. And I might have noticed those like terms to combine. But anyway, this is the path I took. You can take another one as long as it leads to the same result. Okay. This one is a fraction. I cannot cross from top to bottom unless I'm simplifying, making a factor of 1, right? If I can cancel something out, I will. Or I could use negative exponents to switch from the top to the bottom. Check out negative exponents if you don't understand the power of those. So I'm going to rewrite this as its parenthesis with its 1/2 power, and interestingly enough, apply that to each of the pieces here. It is a little bit I-ish, right? But negative 81 to the 1/2 power. Oh, I'm going to write 81 as 9, no, not 9 squared. 3 times 3 times 3 times 3, 3 to the 4th. So I'm going to go ahead and do the prime factorization of negative 81 as well while I'm here. And that's to the 1/2. And then I'm also going to make m to the 5 halves. And then down here, ooh, this is going to have a 1/3 power. So I'm going to replace it with the parenthesis and the 1/3 power. I don't know what 54 is, so I'm gonna have to factor 54. There's a 2, 27, yeah, 27. Oh, and then some 3s. All right, 1. So it is 2 times 3 to the 3rd power. Oof. Okay, so I have in my parentheses 2 times 3 to the 3rd power times m squared, and all of that is to the 1/3. All right, my next step, I have to erase this, sorry, I don't like to erase my work, but there you go. My next step is to distribute this across each of the factors. There's 3 factors being multiplied here. Have you noticed that I use a lot of dots for my multiplication? I've been putting a lot of dots that I don't normally put when I'm doing other math, and I didn't even put it in my final result. But I am reminding myself, who tends to forget, that when I am distributing an exponent to a product, every single number, every single base, this is 50 times x to the 5th, right? So the square root has to go on the 50 and the x to the 5th. That was an intentional move on my part to change the way I write it, to remind myself not to screw that up. So find those tricks for yourself as you're working these problems on Delta Math. So I have now -3 to the 4/2, which is -3 to the 2, right? 4/2 is 2. Oh, interesting. Okay, that's not right. I already screwed it up, and I was just talking about this. This is a factor of -1 and a factor of 3 to the 4. Aha. Haven't seen it that way in a while, right? So technically it's -1 to the 1/2 times 3 to the 2 times m to the 5/2. And now down here I have 2 to the 1/3, 3 to the 3/3, or just 1, and then m to the 2/3. Okay. Now, I don't think my 2 to the 1/3 is going to go anywhere. I don't have another 2 anywhere. So I think it's just going to hang out. But this 3 and this and one of these 3's, 3 squared could be written as 3 times 3, at which point I have a 3 divided by 3 that can simplify to a factor of 1. Could I do that here? Could I rewrite m to the 5/2 as m to the 2/3? Oh, that's so ugly. Now, here's what I'm going to do. I'm going to move this to the top, but with a negative exponent. So this, instead of divided by m to the 2/3, it is times m to the -2/3. Because here's what I can do. Now I can add these exponents. What is 5/2 minus 2/3? Well, I need to multiply this by 3 over 3 and this by 2 over 2. And I get 15 minus 4 all over 6. 15 minus 4 is 11, 11/6. Woo, this is ugly. Okay, I'm gonna erase my factorization to make some room. If you need room on the test, feel free to use the back or ask for scratch paper. So now, I have -1 to the 1/2. Yeah, that's actually I think I may have, an apology to Aiden, sorry. Yeah, -1 to the 1/2. Now here's the thing about it. When there's a variable, the variable could have a negative value that undoes that before you have to take the square root. So we're kind of playing loose and fast with these order of operations. But for right now, we're gonna just write it like this. And then times 3 times m to the, what did we decide? 11/6. And all of that is over 2 to the 1/3. All right, we have all positive exponents. We have all interesting bases. If you want to replace -1 to the 1/2 power with I, that's totally valid. I would take that. So if you want this to be 3 times I times m to the 11/6 over 2 to the 1/3, that's okay. Now, it may not be imaginary again. M is to an odd power, so if m was negative, this would all work out just fine. The domain of this function is only negative m's. How about that? Let's talk about that. Okay, sorry, I've gotten off task. But my final answer is one of these two things. Because all of the numerical bases are prime. All of the bases appear only once with a single exponent, so I've combined all my m's that were in different places. And there are no more radicals. I've turned everything into a fractional exponent and simplified as much as I can. So, done. That was messy. All right. Solve for the equation for the value of x that makes it true, or values that make it true. Okay? So the first step is isolate the radical. Done. The next step is going to be to square both sides. Now here's what's important. This is not x squared plus 3 squared. This is x plus 3. I'm not actually angry, I'm just goofing off. This is not just x squared plus 9. This is x squared plus 3x plus 3x plus 9. So we need that trinomial that comes from the square of this binomial. That was a lot of words, but we have to do the math. It's not distributable across that plus. It doesn't work that way. So we're going to, now that we recognize we have a quadratic, we're going to try and get it to be 0 equals. So I'm going to subtract 2x, combine like terms. I have no x squareds I'm going to mess with. So 6x minus 2x is 4x. 9 minus 14 is -5. Yeah, I think that's right. Great. Now I have a quadratic in ax squared plus bx plus c equals 0 form. Awesome. I get to choose. If I want to assign a is 1, b is 4, c is -5, I can do the quadratic formula. Alternatively, I can try and see if I can write it in factored form. Factored form would say I need these to multiply to -5. My only choices are -1 and 5 or -5 and 1. Do either of those choices add up to a 4x when I do the math here in the middle, right? See the sum, okay? So x squared is x and x. I need to make these two add up to the 4x, and then I have this -5. So I think I need the +5 so that I get 5x here and I only subtract 1x here to make the +4x. So my length and width are x plus 5 and x minus 1. X plus 5 equals 0, or x minus 1 equals 0. That's why I turned it into a box with an area that equaled 0, because that means either the width of the box is 0 or the height of the box is 0. To do that, I need x to be either -5 or 1. Now, in a quadratic, we would be done now, unless we wanted to check our work. But in a radical equation, we are not done. And you cannot get full credit until you identify whether any of the zeros are extraneous. So I know that the numbers -5 and 1 will appear here somewhere. They might both be here, they might both be here, might be 1 and 1. But they'll be there somewhere. So I have to check. I check by plugging into the very original equation. So let's try x equals 1 first. That's easier math. Square root of 2 times 1 plus 14. Ooh, that's the square root of 16. Okay, sorry. And that will equal 1 plus 3. I get ahead. So square root of 16 is 4, and 1 plus 3 is 4. Hey, it worked. It's part of my solution set. Awesome. Now, I don't know if I'm going to have another entry in the solution set or a number down here, so I'm going to leave that open. Remember, my set needs set brackets. Set brackets are squiggles. So now I need to check x equals -5. This one's tricky. You got to watch out for the signs. 2 times -5 is -10 plus 14. Okay, well, that's going to be 4, so the square root will be 2. I got ahead of myself again. Over here, this x also needs to be substituted with -5. -5 plus 3 is -2. Uh-oh. Those aren't equal. So it turns out that x minus 5 must be my extraneous, x equals -5, I'm sorry, must be my extraneous solution. So my solution set is just the 1. Cool. Generate a table of at least 3 values and plot the function. All right, so if you want to talk through of why this problem is what it is, check out the video for quiz A. This is quiz B. But we are going to give our domain and range in interval notation. So this is either going to be parentheses or square brackets. There's going to be maybe infinities involved, but let's get the graph because that's way easier to pull the domain from. So if I'm going to graph, I want to find where I'm going to start. Where does this function begin? The parent function starts at 0, 0 and goes up like this. Half a parabola in the sideways direction. 0, 0 means f of 0 was the square root of 0. The taking of the square root of 0 is the boundary between real answers and imaginary ones that we can't graph. So we want to find what makes the thing under the square root equal 0. That is where our vertex is, just like it was for the quadratic in vertex form, just like it was for the absolute value in transformation form. For all transformation functions, transformation formed functions, we're looking for the x that makes the inside of the parent operation equal 0. So divide by 4, I get 1 minus x equals 0. Add the x, and I get x equals 1. So 1 is the vertex x value. Now to find the y, I have to plug that in. F of 1 is -2 plus, when I put 1 here, I get square root of 0. That was my whole goal. So it must just be that vertical shift down by 2. -2, hooray. That is where my function begins. 1, -2. Now I don't know for sure if it goes to the right or to the left, up or down, whatever, but I can just try another value if I feel like it. I should realize that this function, when I go over 1, I go up the square root of 1. If I go over 2, I go up the square root of 2. That's not helpful. But if I go over 4, I go up the square root of 4. So these, if I go over 1, I go up the square root of 1, which is 1, right? If I go over 4, I go up the square root of 4, which is 2, okay? So I can choose nice values that'll make my graph easier to make, or I can get out a calculator, but that's slower and harder to be sure of. So don't let the calculator slow you down. I'm gonna find what happened. This is my parent. I want to do a quick transformation analysis. This is shifted down, but it's not vertically flipped, but my x value in here is negative. If you do any of the transformation delta math, you'll see that that is a horizontal reflection. So I am not going to be facing that way. This function is going to be reflected that way. That's what a negative in front of my x does. So I'm going to test that theory. I'm just going to plug in some numbers, but I'm going to check what happens at x equals 0 because that is 1 to the left. If I go over 1, I should be able to go up a square root of 1 or whatever the vertical stretch or horizontal compression is. So I'm going to try f of 0. F of 0 is -2 plus square root of 4 times 1 minus 0. Well, that's just 4 times 1. And so that's 2, and -1 plus 2 is 1. So over here at 0, I'm going to be all the way up here at 1. That's a steep climb. Really? Am I sure of that? Oh, I made this -2. That was dumb. Okay, sorry, that was a mistake. That seemed too steep for a... I can see that that horizontal compression here of 4 is actually the same thing as a vertical stretch by 2. So I wasn't expecting that. Okay, -2 plus 2 is 0. All right, interesting. This function goes through the origin. It's not the vertex. In fact, the vertex is here and I can label it now. Now that I've confirmed that it goes to the left, my vertex is 1, -2. So does go through the origin though, that's fun. How about f of, now I'm not going to try -1 because I don't think that's going to work. Instead I'm going to count over 4 because going up the square root of 4 would be to go up 2. So 1, 2, 3, 4 is -3. I'm going to try f of -3 next. In the same way I learned to count out my parabola, I can count out smart values of my square root function in this way. So f of -3 is -2 plus the square root of 4 times 1 minus -3. Okay, we can see why those negative x values are going to be okay, right? All of these negative x values are going to work because they are being subtracted, so they end up looking like they're adding under the radical. So this is now -2 plus 1 plus 3 is 4. 4 times 4 is 16. The square root of 16 is 4. Hooray! -2 plus 4 is a +2. So I need to go over to -3, and I'm going to go up to 2. And I can start to see that concavity downward, it's a fancy word you'll learn in calculus, concave downward action over here, that it starts to slow down in its climb. Technically that's all I need. If I was going to find another point though, I think I would go over by 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's -8. F of -8 is -2 plus the square root of 4 times 1 minus -8. Well, it's the square root of 4 times the square root of 9 is 2 times 3 is 6. Or you could do the math and it's apparently 36. So -2 plus 6 is 4. Oh, -8, sorry. So come over to -8, go up to 4. 1, 2, 3, 4. All right, and I can see that that seems to work with that concave down, sort of slowing down of the ascent. Great. That's what my function looks like. Now, what is my domain? Domain interval notation starts with the least x value that exists. Well, I could keep going to infinity, so I must be, my least value is -infinity. And it exists, and then it stops existing. Its greatest x value is over here at 1. But the 1 is included because it is the vertex. It is on my chart, it has a valid output, it's part of the domain. The range now, least value, well, it doesn't exist. The lowest value is -2. And that -2 exists here. All these numbers are climbing and getting bigger, and they will keep getting bigger all the way to infinity. So That is our domain and range in interval notation. We labeled our vertex, we graphed, we have at least 3 points. I'm loving it. Have a good one.